All right, starting with section 7.4, we're going to look at rational functions, and we're going to look at growing without bound, which again means that your x's are going to keep growing out to infinity. So using a function that we've already looked at, x squared, let's just throw a minus 5 in there for giggles, but we know what's going to happen when our x gets bigger and bigger and bigger. All right, I just want to practice this technique with tables in your calculator so we can practice it with other functions, and you'll be practicing it again when you get into Calc 1. So when you get to a homework problem, and these are all going to be text boxes and you have to fill them in, what you don't want to do is have to plug in these numbers and do these all by hand. So we're going to show you a nice technique here in your calculator. So grabbing my calculator here, we're going to go to y1 and we're going to type in x squared minus 5. Now, the next thing we want to do is we want to go to second window to your table set. We're going to make a change here. The problem with filling out this table is that your x's are not counting by the same value. Increased by 9, 90, 9,900. All right. So we can tell the calculator what x value we want you to use, and then the calculator will tell us what y coordinates to put in those text boxes in the homework. All you have to do is change the independent variable, that's your x, change that to ask. Now when you hit second graph and you get the table, we can start entering the numbers. So here x is a 1, I'm going to type in a 1, there it is, and then hit enter. And it gives me a negative 4. And my next number is a 10. We can type in the 10, we get 95. Let's see, the next number is 100. We get 9,995. Then we have 10,000. Ooh, now we get 1 equal 1E8. Well, what does that mean? Well, if you move your cursor to that number, it'll give you the number down here. So here we have 1, 2, 3, 4, 5, 6, 7 nines. And let's see, our last number, what is that, 1,000,000? 1, 2, 3, 1, 2, 3. Enter. Again, looking over here, there's all my digits. And so we'll type those in. So have that available so we can type that into your calculator. All right, so I'm going to put that over here on my other monitor here. Here we go. Click, click. We'll get caught up filling in our text boxes. So what do you notice about the values of f of x as x gets larger and larger? Well, at first, the y went small to negative, but then when we start putting bigger x's, now when we're squaring that big number, now we get even bigger numbers. So my f of x values are getting bigger faster than what the x values are. So that definitely tells me, okay, then f of x has to be approaching a specific number, which is going to be infinity. So as x gets larger without bound, so does your y's. They're heading off to positive infinity. And then you can use your calculator again for the negative numbers. So if we look at our table and we start putting in negative numbers, negative 1, negative 10, negative 100, and it appears that we're still getting the same numbers. And of course, go ahead, we'll fill those in our text box here. The negative 4, the 95, the 9,995, and it's the same numbers that we had before because we are squaring the x squared, so we're turning them back into positives. So again, as x goes to negative infinity without bound, so does our y's, except now our y's still go to positive infinity instead of negative infinity, which again, this does make sense because when we're looking at our parabola, we notice that the left and right hand behavior both go up to positive infinity for your y's. And this is just, again, an example of the table justifying and finding limits. All right, so if we practice this now, let's say a rational function, say 1 over x. Now, here's something that's nice about your calculator that, if my x's are going to be the same, you go to y equals, you clear out the function. Now we put in 1 divided by, well, I'm going to do two things here. Alpha y equals, let's go with the fraction notation. And let me check my mode. Okay, my answers are in decimal mode. So if you leave it in auto and you type in that fraction, you'll get fractional answers in that y column. But if you leave it in decimal mode, you'll have decimals here. So we can start to type in our answers. So let's see, if you notice that it adjusted for the new function. So when x was 1, y will be 1. When x is 10, we have 0.1. When x is 100, we have 0.01. Now that you have 10,000, that's 1e to the negative fourth power. That's scientific notation, which means that this is 1 being multiplied by 10 to the negative fourth power, which means you move the decimal point 4 places to the left. We'll move this one 6 places to the left. So filling in my text box here, 1 0, 1 decimal point, 2 zeros, 2 decimal places, 4 decimals, 3 decimal places. Or I should say 3 zeros with 4 total decimal places. So you can count the zeros, that's how many place values when you divide by 10. 1, 2, 3, 4, 5, 6 zeros. We're going to need 5 zeros. Then the 1 to get our 6 decimal places. So there is a tendency here that every time you tack on a 0 to your previous x, so from 10 to 100, we put in 1 0, you put a 0 in front of the 1. 1, 2 zeros, now I have 4 zeros for a total, so we put in 2 more zeros after this. So every time you put in a 0 after the number, you're putting a 0 decimal place in. It's just all about counting decimal places. And yes, we appear to be going to a specific number. We're getting smaller and smaller and smaller. We're approaching 0. Can you find a specific value for x when f of x is less than 1 billionth? Well, let's see. When I had 100, it was 100th. 10,000, it was 10,000ths. 1 million, 1 millionths. So if I want to be less than 1 billionth, I have to have a number that's bigger than 1 billion. And let's see, D, using the ideas discovered here, what number, if any, do you think the following expressions would approach as x grows without bound? Again, same concept here with these functions. Well, the first thing I noticed is that the numerators are all constants, whether they're positive or negative. And now I still have x's in the denominator, but these are now squared, cubed into the fifth, which means, okay, these numbers in the bottom are going to get bigger faster than what I have on the top. But then when I divide that into a 1, my decimal is going to get smaller, and I'm going to approach 0 even faster. So the same thing's going to happen as in 1 over x. It's just that we're going to approach 0 much, much faster than what we're doing up here, because we're making the denominators even bigger without changing the value of the top. If we do negative numbers, okay, here's our table that we had so far. Let's check a 0. You put 0 in for x. That's going to give me something that's undefined. And when I now put negatives in, my decimals will pretty much be the same, except we now have negative values. And I'll tell you what, I don't know what happened here. I got 1 million here, but I have 100,000 here. I better check my decimals. 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, they're all good. Okay. Just didn't want to have a cut and paste error there. So as x approaches infinity, we already said we're going to 0. And now when x goes to negative infinity, we're still going to 0. So if we wanted to make a quick sketch of this, we have a horizontal asymptote. When I start heading out to infinity, we're going to 0. Y equals 0 is your x-axis. And then when we're at 0, we're undefined, so we can't touch the y-axis either. So if I count this up, 1, 2, 3, 1, 2, 3, I'm not going to try to count out to 1,000 or 10. That's crazy. but 1 over 1 is 1. And then when x is 2, I'm at a half, 1 over 2. When x is a 3, I'm 1 over 3. So I would say we'd always start at 1, 1, and then just kind of curve down to the x-axis, and then we curve up to the y-axis. And you're going to get the same picture over here in quadrant 3. Start at -1, -1. Whoops, go back. Approach the x-axis, approach the y-axis. So for your horizontal asymptote, anytime you have p over x, q over x, and again, I like to use n over x, d over x, numerator, denominator. If x is approaching some constant value, as x goes to infinity or negative infinity, then the line y equals b is a horizontal asymptote. And what's interesting about this particular definition is that our example said we're going to 0, which is a real number. So if they're saying b, there's a chance that we can go to different horizontal asymptotes, maybe a +2 or a -1. Those are all possibilities. So if we started putting in really small numbers, because again, I want to back up here real quick, is what happens when we're heading towards the 0. So now we know we're undefined, but if I try 1/10, I get a 10. 1 over 100, I get 100. Wait a minute. Oh, I get it. 1 over 10 goes in for x. I'm trying to divide by a fraction, but we don't divide by fractions. We multiply by its reciprocal. So 10 times the 1 is just 10. The reciprocal of 1 over 100 is 100. Okay, so I got it. Okay, so real quick, this would be 1,000, 10,000, 100,000. So what appears to be happening is that as we start to approach 0 on our x, when we're getting closer and closer to 0, my y's appear to be approaching infinity. I'm getting bigger and bigger. Now, there's a special notation for what my table is doing. I'm approaching 0 from the positive side, the right side. So you will see this notation, especially when you get to calc, when you're doing limits. X is approaching 0, and in the exponent position, they put a plus sign. That means you're approaching it from the right-hand side of 0. And as we were doing that, we said we're getting bigger and bigger values, so we're increasing without bound, which means, okay, we're approaching infinity. And then for j, again, if we want a value 1 over x that's greater than 1 billionth, we want to put in 1 over 1 billion, but we want to put in something less than that to make something bigger. Because remember, we're going to multiply by the reciprocal of that, so that overall value becomes a billion. So if I put in 1 over 2 billion, I flip it for 1 over x, and now 2 billion will be greater than 1 billion. All right, so what's happening here, as we get closer and closer to 0, from the right side of 0, f of x is approaching infinity. This is to say that as x approaches 0 from the right, and we can also look at this from the left, so we'll take a quick peek at that too, then f of x is approaching infinity. This is called a vertical asymptote. And so here's our formal definition as our rational function. If your y's are approaching infinity, as x approaches a, then x equals a as a vertical asymptote. Now, it's just putting absolute value bars here saying, okay, it's going to be positive y's. But we could have negative y's, which means then we're going to negative infinity. That's possible too. They just do that to shorten down what they have to type in. Okay, so now we have our vertical asymptotes definition. Let's go back to that original graph we had a couple slides ago and looking at the picture, explaining what's taking place. So again, as my graph, here's my x's. Now we're approaching 0 from the right. As I approach this vertical asymptote, I have to decide, am I going to turn up or am I going to turn down? Well, if there's no x-intercept here, then I have to turn and I'm going to head up to positive infinity. As I approach from the left, as I get to 0, again, no x-intercept making me turn up, so I have to turn and I'm going down to negative infinity. So again, as you approach a constant from the left and from the right, you either one side goes up, one side goes down.